Okay, another problem computing a definite integral. This one's going to be a little bit tougher, at least in the sense that we can't use geometry. Okay, so here's the problem. This is number 17 in the book. They give you this curve. They tell you the function that we see here at the top is y equals 1 over x squared. And they want us to find the area below this curve between 1 and 2. Okay, so as a definite integral, we could write that. And again, I like to call all of my definite integrals A, because we're computing an area. At least when we're computing an area, I like to call them A. So what is this area? Well, we would represent it as the integral from 1 to 2. Okay, you put the smallest number on the left first on the bottom. The bigger number on the right goes at the top. It's the integral of 1 over x squared, okay, because that's the function we're looking beneath. And the integral is with respect to x. Okay. Now, of course, why can't we use geometry? Okay, well, we can't use geometry because, unlike the last example, the top of this function isn't a line. Okay, it's some kind of a curve. If this was a straight line, yeah, we might have a triangle and a rectangle again, but this is definitely not something like that. And this curve, it looks, nice and smooth, but it's not part of a circle. It's not a shape you recognize. So some new shape, who knows what the area is? You can kind of make an educated guess of what the area is. Now, if you look on my graph and notice this, that just to kind of zoom in a little bit, I made every 3 grid boxes 1 unit. So a 1 by 1 box would be something like this. Okay, so this is going to be less than 1 square unit. It's going to be pretty small. Okay, but what is it exactly? Okay, well, we have to use the fundamental theorem of calculus on this one because we can't use geometry. Okay, so here's how we're going to evaluate the definite integral. We're going to use the fundamental theorem of calculus. And again, here's what it says. If you want to calculate a definite integral, okay, using calculus, all you have to do is find this function big F. Okay, you're integrating little f. We're going to find a function called big F. And in that function, you just have to put the upper limit in and the lower limit in and subtract. Okay, but what is that function big F? That's the whole neat thing about the fundamental theorem of calculus. It says to get this answer, which is just putting a number into a function twice and subtracting, you just need this function, which can be any antiderivative of the one under the integral sign. Okay, so if you look at what we had, the area that we wanted to compute was the integral from 1 to 2 of 1 over x squared dx. Okay, so for us, this thing is the little f of x. That's the function whose antiderivative we need to find. Okay, so here's the way we write this out. We want to keep track of everything because we really have to do 2 things. We have to find an antiderivative, and then we have to put some numbers into it. Okay, so antiderivative means indefinite integral. Okay, we know the things we were doing before we put numbers here. Okay, so I need to think about what is the indefinite integral of 1 over x squared. Okay, so when you're doing a definite integral, you first do an indefinite integral. Okay, we have to integrate this function to get one of its antiderivatives. Okay, so if you recall, the first thing we would do if we were integrating this in a couple sections ago is we would want to use that power rule for integration. So we need to write this as x to the power negative 2. Okay, so the next question is, okay, what function is an antiderivative of this? Okay, well, to find a function whose antiderivative, to find a function that is the antiderivative of x to the power negative 2, we use that power rule. And the power rule for integration says you take 1 over the old power plus 1 times x to the old power plus 1. Okay, so that right there is big F of x. Okay, that's the antiderivative. We just need to simplify that. Okay, now here's where the notation needs to be. We need to be kind of careful with. You see, we found the antiderivative of x to the power negative 2. If you look at the fundamental theorem of calculus, of course you have to put numbers in that antiderivative. So to indicate that we have that yet to do, I'm just going to put parentheses around this whole thing and put a little bar here. I'm going to put the numbers 1 and 2 there. Okay, that's just a little reminder for me that I have yet to substitute the endpoints from the definite integral into this function. Okay, so let's keep going here. We want to simplify this function a little bit because I just used the power rule. Well, that's 1 over, well, negative 1. Okay, so it'll be negative x to the power negative 1. Okay, which you can certainly write as negative 1 over x. Okay, And notice I keep this bar with me because it's just a reminder that I have yet to put the limits into this antiderivative. Okay. Now, here's what we do. Okay, we've got the function whose derivative is 1 over x squared. Okay. Sorry, we have a function whose derivative is 1 over x squared. And again, you notice that when we do definite integrals, we don't need that plus c. Well, we don't need it because we're not trying to find the most general antiderivative. We just need any antiderivative. Okay, that's something else I wanted to mention here. You notice the word any here. What do they mean by that? Well, they mean basically you don't need to worry about a constant that could be anything. You know, if you use negative 1 over x plus 7, you'd still get the same answer. So we just let that constant be 0 and work with this particular antiderivative of 1 over x squared. Okay, so all we have to do now is substitute these numbers into the antiderivative we found. Okay, so the upper limit goes first. Okay, we put negative 1, so we got negative 1 over 2. Okay, and then we have to subtract what we get when we put the lower limit into this function. Okay, well, that's 1. Okay, so what you see me writing right here, okay, that right there is f of b minus f of a, big F here. Okay, so we found the antiderivative, we put the upper limit in first, then the lower limit, and now we're subtracting. Okay, well, that's negative 1/2. Here I've got 2 minus signs, so that'll be plus 1, and it turns out that is exactly positive 1/2. So the area of that region is 1/2 of a square unit. Okay, so let's go back and look at it again. Okay, well, you know, you could convince me of that, I suppose, right? This is 1 square unit, and the area we're looking at looks like it is about half of that, so the answer seems reasonable. But you know, it's not something you could say with full confidence because we haven't, you know, divided the region in half in an obvious way. I mean, it's just this little shape that's something less than 1 square unit. Well, it turns out it's exactly 1/2 of a square unit. Okay.